All right, so welcome everyone to today's class. Good to see you made it. As you can see, obviously not much is working in this room. The only thing we have is the projector, and I do hope there is a decent live stream as well. I don't have a camera today, so there's just the iPad slides. I also don't have a microphone today. It's not working in this room. So I'm using my notebook to record the audio for the live stream. I hope that still works, at least decently enough. In case you can't hear me well, feel free to move to the front rows. Good. So, very quick recap. As you hopefully remember, we've talked about constraint optimization on Monday. Here's the first problem type that we dealt with. We want to minimize a function that is usually differentiable, subject to a number of equality constraints, and we capture those equality constraints in another function that might have a vectorial output. Right? So you just combine all these equality constraints into one function, one output row per equality constraint, basically. The f function, of course, the objective has just a real number as an output. We want to minimize that, so a vector doesn't make a lot of sense there. Okay, generally we always minimize. Of course, you can also maximize by just minimizing negative f. And the way to deal with this type of problems was the Lagrange multipliers method. And that says if we have an extreme point of a function over the feasible region, call that capital F here, and that feasible region is defined by all points that satisfy the equality constraints. There exist so-called Lagrange multipliers. Usually denote those by C. One multiplier, one real multiplier per constraint. And those fulfill this Lagrange condition here. So you have the gradient of f plus the Jacobian of h times that multipliers vector. That needs to be 0. Right, so the way to find those extreme points in the constraint setting is usually to look at that. That will give you a number of equations that you need to solve. The solutions for those will give you candidate points. And then, of course, you need to make sure that there is actually a minimum of that function. Usually the argument is f is a continuous function. And the feasible region is compact, so it's bounded and it's closed. And then we know there is a minimum. F assumes a minimum on that feasible region. So we can be sure that one of those candidate points will actually be a minimum. But usually we just compare the function values to see which is the best one in terms of our objective. We've also talked about a more general setting where we're adding inequality constraints. And there's a more general theorem that characterizes the candidate points for optima subject to this more general setting. This is called the KKT theorem. And what we said was if all those functions are nice, basically meaning continuously differentiable, then a minimum over the feasible region of f always is a KKT point. And a KKT point that contains the point itself and two types of multipliers. We use letters y and c for those. Y are the multipliers associated with the inequality constraints. C are the multipliers associated with the equality constraints. For those C multiplier is basically the same thing as before holds. You get an equation that's a little more general. So again, that's the gradient of f. That's this part is familiar, right? JH times the C multipliers. Plus, and now you add a term that looks very much the same as this C part here for the inequality constraints, where you use the Jacobian of G, the inequality function, times those inequality multipliers. Again, that gives you a couple of equations. Then you need to make sure that your point is feasible. So inequalities and equalities need to be satisfied. And then there's two more points that only need to hold for the inequality multipliers. Those multipliers need to be non-negative. And this scalar product here needs to be 0, or in other words, probably better to capture. If you consider an inequality and a multiplier, then either that inequality holds with equality, so G is actually 0 at the point x star, or the multiplier is 0, or maybe both. Right? One of that always needs to be satisfied. And that's called the complementarity condition. Okay, that's only true for the inequalities and the corresponding multipliers. You don't have constraints of that type for the equalities and their multipliers. Also in that case, all of that is tailored towards minimization, right? So that only works for minimization problems. The Lagrange idea basically also works for maximization. You don't have to modify that. In that case, it doesn't work anymore because you would have to change the sign of the multipliers for a maximization problem, right? So what you should do is, if you have a maximization problem, transform that to minimization first, simply by negating the objective function, and then use that new problem to formulate the KKT conditions here. Right? So in particular, all the candidate points that you're getting from this are then candidates for minima only. Right? So if you compare them and then find one of them has the maximum function value, you can't conclude that is a maximum. That's usually not true. For just the Lagrange approach, that is true. All right, so that's the theorem of Karosh, Kuhn, and Tucker. We discussed those last time. So today we'll have ample time for problem solving. I thought we'd just start with one of the more recent exam problems here. So that's a problem from a 2021 exam on constrained optimization. I'll give it some time to work on that. And let's see what you come up with as a solution. you have any questions, don't hesitate to ask. It's a small room here, so I can get to you with any questions. One more remark for those that have already done ABC. If you get to D for today, it's sufficient to show that this is a candidate point for an optimal solution. To show that this is actually an optimal solution is one more fact that we're going to talk about next week. Oh yeah, we took them last time. So in this case, we have legal equality. So that's the static form of the equality. G function. And that is R3. And for each of those, we have a multiplying group. Okay, so one multiplying group in equality. So that means we get 3 multipliers. That's the vector of multipliers. So the y here is actually a vector. It has 3 numbers.
So here, those 3 things that are G, they express as fraction.
Yeah, exactly. So that is so we're going to do 3 numbers.
So we represent y as this.
Exactly. Haben wir jetzt in jedem Fall 3 Nebenbedingungen, also 3 Ungleichungen. Die bringt man erstmal in diese Standardform, sodass die alle kleine gleich 0.
Sonst eine Zahl.
Genau, und eventuell wäre es dann angenehm, oder auch die positive.
Okay.
Das ist eine Größe, die muss man teilen.
Die Rot angenommen.
Genau, wenn sich zwei Größe gleich, dann müssen immer kleiner gleich wie der Kinder.
Also deswegen muss ich teilen.
Immer mit der Seite so ungefähr und mindestens 1 2
Okay, das ist das ist das X ist nicht wirklich.
Erstmal das hin, die Jeder was sind. Jetzt formuliert man das einfach erst eine Ungleichung auf einer Vektor. Und sagen, das ist der Weltmaß ist das nur das aus der Absicht von G. G ist dann die Funktion, die Variable, x1, x2 abbildet die linke Seite.
Schon noch kurz mal so. Schreibt man das dann noch als Vektor? Nee.
Doch, das ist die linke Seite die Zeichenvektor. Und das H würde jetzt genauso funktionieren, wenn es auch Gleichungen gibt. Wenn es Gleichungen gibt. Also das H macht dasselbe für die Gleichungen, aber die würde man das zuschreiben, dass dann immer gleich 0 steht. Und dann ist die linke Seite an sich das Gleichungen. In dem Fall gibt es keine Gleichungen, also gibt es auch keine.
Wie kannst du das hier?
Very quick progress check. Who's done with A already? Quick show of hands, please. Who's done with B? Who's done with C? And who's done with D? Okay, yes, we need a couple more minutes for our audience to catch up. For those that are done already, there is a quick tweetback quiz asking you for your rating, difficulty rating of that question here. So here's the tweetback link once again. Let's say we'll take 2 more minutes, and then we'll discuss this problem together. All right, so let's take a look at that problem together. Just out of curiosity, who of you thinks they solved the problem? Just a quick show of hands, please. Wonderful. All right. So as you can see, this was an exam problem a few years back. And as you can also see, there's 21 credits to this problem for an, I think it was an 80 credit exam. So that alone was about a quarter of the exam already. It was one of the harder problems. It was meant to be one of the harder problems. But I think if you prepare well, you should still be able to solve that with not too many problems. So let's quickly gather our facts here. We have this objective function c, right? Looks like this, that we want to maximize. And here is the constraints. First question is, does C attain a maximum over F, where F is the feasible set given by these inequalities? Well, obviously, C is a continuous function, right? So that's the usual argument. We're trying to make that. So for A, C is continuous. And then we need to argue that F is compact. Well, what does F consist of? If you look at those two inequalities, right, those basically define half spaces in R2. So what we have here is something that looks like that. Let me quickly sketch that. So a half space, a linear inequality in the two-dimensional plane. You know, if it was an equality, that would define a line, right? So something like that. I'm not saying this is one of those lines, just a general line. And then if you turn that into an inequality, that means you consider all the points, not just on the line, but also on one of those two sides, yeah, depending on which direction this inequality has. And you'd call that a half space, right? So something like that. A half space is obviously closed, right? Because if you remove that from R2, you get an open set. It's not usually bounded, however. So what we have here first is an intersection of two half spaces. So that might look something like that. All right, so two half spaces intersecting might produce a set like this. Of course, the intersection of closed sets is still closed, so no problem with that. The boundedness is not guaranteed by that already. But this first equation, or this first inequality, that takes care of the boundedness. Does anyone know what that is geometrically? Yeah?
It's a circle.
It's a circle, exactly, or a disk rather. So the circle line and the interior of that. And so what you get here is a circle. That circle is centered around the points 1 and in x2 direction 3. Right, so that's around the point 1, 3. And the radius is 2. Right, pay attention to that. We have these squares here, so that is the radius squared. And of course, the circle is obviously bounded. Right, so you also have something like 1, 3 somewhere here, something like that. That disk here, and that's bounded. And of course, also closed, right? So you intersect 3 closed sets, and one of them is bounded, so the result is sure to be closed and bounded again. Right, so C is continuous. F is the intersection of 2 closed half spaces and again closed and bounded disk. So that means F is compact. And that means C attains a maximum on F. Right, so that answers A positively. Any questions about that before we get to the next part? Yeah.
Would there be a need to sketch these three functions in exam, or only to write those?
Sorry, I didn't get the.
Is there a need to sketch the functions?
Is there a need to sketch the functions? No. No, just this answer here in writing, that would have been sufficient. You don't need to sketch those functions. Of course, you can if it helps you, but it's enough to recognize what nature these inequalities are, basically. Yeah, so you should recognize a half space, and you should recognize a circle or an ellipse when you see it. Good. So B, basically that's the preparation for the rest of the problem. Rewrite the optimization problem in the usual form, meaning minimize F subject to H equals 0, G is less or equal to 0. So basically we need to define the functions F, H, and G properly. Notice we have a maximization problem here, maximizing C. So we first need to turn that into a minimization problem. Right, so the first thing we do is we want to minimize a function f of x with, well, f of x is the negative of C then, and that is simply x1 plus 3x2. We don't have any equality constraints, so we don't need an H function. And for the inequalities, basically all we need to do is we need to reformulate them in the correct way. We want to turn this into something that can be formulated as g of x1, x2 is less or equal to 0, where 0 is the 0 vector of correct dimension. So we need to turn these inequalities, we need to reformulate them such that they read something is less or equal to 0. And then that something on the left-hand side is basically our g. Right, so let's do that. First one is almost correct already. So this is x1 minus 1 squared plus x2 minus 3 squared is less or equal to 4. And we reformulate that by just taking the 4 to the left side. So this is minus 4 is less or equal to 0. Then we have x1 plus 2x2 is greater or equal to 5. Again, start by taking the constant on the left. So minus 5 is greater or equal to 0 to get the correct right-hand side. And then we just multiply by minus 1. Right? And for inequalities, remember multiplication by minus 1 changes the sign. Right? So you get less or equal to instead of greater or equal to. So multiply that by minus 1, change all the signs here, and turn that around to be a less or equal to. And we'll do the same thing with the last equation, greater or equal to 2. So first we take the 2 to the left, and then we multiply that by minus 1. Right? Change the signs here. Change that inequality sign here. Right, so that's the reformulation, and then all we have to do is just take this left-hand side here, and let be our g. Right, so g of, we have two variables, g of x1, x2, So that is x1 minus 1 squared plus x2 minus 3 squared minus 4. Then we have minus x1 minus 2x2 plus 5 and minus x2 plus 2. And the condition is this is less or equal to the all zeros vector. We have 3 rows, so the right-hand side is also 3 zeros. Yeah.
I'm unsure about the bounded part. Could you give an argument why it's bounded again real quick?
Well, it's bounded
Yeah.
because we intersect. So we need something that fulfills all inequalities. So basically the feasible set is the intersection of the feasible sets of each inequality.
Mm-hmm.
Right? Everything that fulfills all inequalities at the same time. This inequality here defines a disk. Yeah, that looks something like this. A disk is bounded.
Mm-hmm. Okay.
So if one of your sets is bounded and you intersect, then of course you can only select points from that disk, so the result is going to be bounded.
Okay. So the other functions are nearly not relevant.
That depends on what that setting really looks like. So this is not how the lines actually look, right?
Yeah.
Basically what you will get is that disk and then cut part of the disk out. That's what the others will do, probably. Right, any more questions? Yeah?
In the program statement, there is the sentence, do not forget to provide explicit definitions. What are explicit definitions exactly?
So with explicit definitions, I mean your solution should contain something like that. The function g is defined as. Right? Don't just write that.
Okay.
I wouldn't have been satisfied with that. Yeah.
We also need to note that there are no equalities, so h of x is equal to 0.
You should comment about this no inequality. So either you should say something like no h is required or h is 0, whatever you prefer. Both is fine. Yeah, but some comment about that should be made. I think that was worth 1 point or something. Any more questions? Good. So next part. C, write down the KKT conditions for the optimization problem. Let's copy that over once again here. So as a reminder, these here are the KKT conditions. And now we need to apply that to our problem at hand. Remember, f is this function here. So we need the gradient of f, and we need the Jacobian of g to use this function here. So let's first compute those. Right? Gradient of f. Let's see, x1 plus 3x2, so differentiating with respect to x1 yields a 1, and x2, that yields a 3, so we have a constant gradient here. And for the Jacobian of g, right, this is what g looks like here. So we just differentiate each of those rows separately with respect to x1 first, and then with respect to x2. So let's see. For the first row, we get 2x1 minus 1. And there's no other x1 in there. So that's all. And for x2, we get 2x2 minus 3. Then for the second row, we get a minus 1 for x1 and a minus 2 for x2. And for the third row, we get a 0 and a minus 1. Yeah, that should be correct. And then we're ready to write down the KKT conditions here. So remember, there's no h, so this part We just don't need that. For the y vector, the multipliers, we have 3 inequalities, so that means we have 3 multipliers. Three inequality multipliers. So let's call those y1, y2, y3. And then we can write down this condition here. So gradient of f plus Jacobian of g at x1, x2 transposed times y is the all zeros vector, and we get 2 rows here, obviously, because the gradient of f has 2 rows. Right, so what we have is, let's write that down in vector form first, 1, 3. Then if we transpose that Jacobian here, we get 2x1 minus 1 and 2x2 minus 3 minus 1 minus 2 and 0 minus 1 times y1, y2, y3 is 0, 0. So if you write this as 2 equalities, one for the first row, one for the second row, we get 1. So start here, right? This one first. Then we multiply this row with the y's. So we get plus 2y1 x1 minus 1 minus y2 plus 0 y3 is 0. And for the second row, we have this 3 here. And then we multiply that second row with the y's. And that yields 2y1 x2 minus 3 minus 2y2 minus y3 is 0. Right? So that's the first part of the KKD conditions. Let's copy that over once again. Right, so we're done with that. Then, of course, we need feasibility constraints. Basically, that means let's just copy the inequalities once again. Those inequalities were, let's see, x1 minus 1 squared plus x2 minus 3 squared minus 4 is less or equal to 0, minus x1 minus 2x2 plus 5 is less or equal to 0, and minus x2 plus 2 is less or equal to 0. Right, so that's the inequality constraints. No equality constraints, so those are done as well. Then we need the multipliers to be non-negative, this condition here. So, well, y1 is greater or equal to 0, y2 is greater or equal to 0, and y3 is greater or equal to 0. And then we need this complementarity slackness constraint here. So 1 constraint per multiplier, or per constraint. That means we get 3 equalities once again. So what we get is y1 times, and now we take the left-hand side of this first inequality here, multiply with that, x1 minus 1 squared plus x2 minus 3 squared minus 4, that is 0. Then y2 times the corresponding condition, this one here, minus x1 minus 2x2 plus 5, that is 0. And finally y3 times this condition here, minus x2 plus 2 is 0. Right? So that's constraint number 5. And looking at the numbers as well. So this here, this is the first condition, that's the second one. There is no third one, right? No H, no third condition. This is 4 and this is 5. All right? Any questions about this part? Yes?
If we don't have part D in the exam, it's sufficient that we don't open the matrices, right? I mean, we don't really need to write in that form, but we can just...
You could write it in matrix form, yeah, that's fine, yeah. Usually I just prefer to write it in that way because usually I will have to solve these equations, and then it's probably more convenient to have it in explicit form. But if you don't want to do that, it's fine to leave it in matrix form, yes. Any other questions? Then let's finally take a look at part D. Remember what that was about, part D here. Question was, is the point 1, 2 an optimal solution? Or rather, is the point 1, 2 a candidate? Could that be an optimal solution? And of course, what you need to do here is take this point, substitute it into the conditions that you just wrote down, and hopefully see that they're satisfied. Then that means you have a candidate point. Or you could also see that they're not satisfied. That means it couldn't be an optimal. That would also be a valid solution, of course. One of these two is bound to happen. Let's see. So we take that point. We substitute x star, that was 1, 2, into the KKT conditions. And it was this 1 to 5 from C. Well, what do we have to do here? First, we need to see that these equalities here are satisfied. So maybe let's just copy that part here. And then some more space. Ah, damn it. Okay, so if instead of x1 you're using 1 and instead of x2 you're using 2, that becomes 1 plus, let's see, if x1 is 1, this becomes 0, plus 0, minus y2. And here we have 3 plus 2y1, x2 minus 3. x2 is 2, so x2 minus 3 is minus 1. So we get minus 2y1 minus 2y2 is 0. Right, so we have those equalities. It's still, we have to find the right values for this y1, y2 here. Oh, sorry, I forgot the y3, right? Need to copy that as well, of course. Minus y3 is 0. Okay, so we still have to find the right values for the y's, right? We only get the x. And now the challenge is to find the right values for the multipliers. If we can do that, fine. If we can't do it, we know it can't be a candidate point. Right, so in that case, obviously this first equation here, that already gives away y2. Right, from that, we immediately see that y2 has to be 1. And of course, we can directly use that down here. So this is 3 minus 2y1 minus 2 minus y3. And well, 3 minus 2 is 1, right? 1 minus 2y1 minus y3 is 0. We can't solve for the other y's right now, but at least y2 is out of the way. Okay, so that was condition number 1. We still have a couple more, so hopefully we'll get values for y2 and y3 as well. Second condition is where we need to check feasibility. That just involves the axis, so that should be easy to do. Let me copy that. So if we substitute the axis here, what we get is, well, 0 plus 2 minus 3 is minus 1 squared minus 4. Well, 1 minus 4 is minus 3, and obviously that is less or equal to 0, right? So that's correct. Then here we get minus 1 minus 2 times 2, this is minus 4 plus 5. So that's minus 5 plus 5 is 0, and that is less or equal to 0, so that's correct. And here we get minus 2 plus 2, again 0. And again, that is obviously less or equal to 0. Right? So the point x star is feasible. There's no equality constraints, so no number 3 to check. For number 4, where we don't yet know the values for the y's, but maybe let's still copy that over. We know one value for the y, so we can check that. We know already that y2, remember y2 is 1. That is greater or equal to 0, right? So that's correct. If y2 would have turned out to be negative, we could have stopped at that point. For the others, we don't know yet, so we'll have to check that later. And first take a look at the conditions number 5 here. Okay, for those you will remember, we have already evaluated those left-hand sides here when we checked the inequalities right there. We found those last two to be 0 and the first one to be minus 3. Right, so that was minus 3. That means this thing turns into minus 3y1 is 0. And obviously that means, well, y1 can only be 0 then. y1 is greater or equal to 0, so that's good. So we're left with y3 basically. Those two here, those were both 0, so we don't get any information about y2 and y3 from that system. That could be anything. But we still have the equality from 1 here, right? Remember, we didn't use this here yet. So we should. Let's copy that over. Okay, so from 1, we know this here. And we also know y2 is 1, and we now know y1 is 0. Yeah, so let's use that. Then we get 1 minus 0 minus y3 is 0. So that means y3 is 1. And that is also greater or equal to 0. So altogether, that means this x star equals 1, 2 with y star, we just found that. Y1 was 0, y2 was 1 if I'm not mistaken, yes, and y3 is also 1. So that means these two fulfill the KKT condition, so that means that is a KKT point. And thus, that is a candidate point for an optimal solution. Okay, so basically you take all you know, you substitute it into these conditions, and then you try to figure out what you don't know. And check whether all of these equations and inequalities actually are satisfied. If they are, you have a candidate point. If they're not, you don't have a candidate point. And that means there is no valid multiplier, so x star couldn't have been a candidate point. Right? In that case, it is. Maybe just to complete that discussion, so you remember the original question was not to show that it's a candidate point, but to show that it is an actual optimal solution. For those that have already watched next week's videos, the argument that's still missing here is convexity. So you would have needed to add that both the objective function is convex and all the constraints are convex. And for a setting like that, you know that each KKT point is also an optimum, a global optimum actually, on the feasible region. Right? So that was the argument I would have expected to complete part D. All right. Quite some work to do, as you can see, but I mean, it's worth 21 points, so I can expect some work, I guess. Any questions about that one? If that's not the case, we might have time for one more. Let's see, which one do we want to do? It's a similar one in the problem, so maybe let's do this one here. And again, so pretty similar to the last one. And again, please, for the last problem C, in this case, just prove that this is a candidate point. What is missing, of course, is again a convexity argument. once you're done, I'll again be interested in your assessment of how hard that problem was. So there's another tweetback quiz asking you for that. Usual question, who of you is done with A already? Who's done with B? Who's done with all of it? So maybe let's take 2 more minutes. Again, I'd appreciate your assessment, so please log into tweet back quickly and let me know how hard you found that problem once you're done. closed and bounded. Dann gibt es immer so eine bestimmte Funktion, dann gibt es immer so. Das liegt, ich kann es trotzdem erzählen. Kann irgendwie ausschließen. Aber ich bin nicht mehr sicher, ob es All right, so maybe let's take a couple minutes to discuss that. So one thing I've just been asked about, you'll notice that in the former problem, we had a question to show that the optimum actually exists. This is missing here, and that is for a reason. Those two constraints here basically have the same form as the two last constraints of the last problem, right? So again, if we reformulate those slightly, let's just do that quickly. You would rewrite that as x1 plus 2x2 minus 12 is less or equal to 0. And the second one would be 2x1 plus x2 minus 12 is less or equal to 0. So geometrically, what you have here is, again, two half spaces. So I don't know the exact form of those half spaces, but that will probably look something like this, right? So your feasible region, oops, and now I messed up. Can I move that? No, I can't. Great. So your feasible region, let me draw that again. Oh, it's back. Very good. Your feasible region will look something like this, probably. That means it's still closed, but it's not bounded anymore, right? You'd need at least a third constraint to make that bounded. That could be an issue, but it doesn't have to be. And that depends on the objective function, of course. Assume we have a linear objective function for just a minute. Basically, that means we optimize in a certain direction and want to move as far as possible in one direction. If that direction happens to be that one here, for example, obviously we will hit that border here at some point, and that will then be the optimal point. So there might still be an optimum. If the direction would be this here, obviously we could move as far as we wanted and never hit a border. And then, of course, that would mean the function is unbounded, so there is no optimal solution. Both might happen in a situation like this, right? So in this case, we couldn't prove up front that there is, sure, an optimum, but there might still be one. Of course, the function here is not linear. That's a nonlinear function, but basically the same problem might apply here, right? And that's why that first part is missing. You just can't do it. All right, brief discussion of how to solve this. Again, in part A, we reformulate the problem in the right form. So basically, I wrote that down already. So for part A, this is already a minimization problem. So our f is exactly the function that is after the minimize. And just copy that. Right, that is this function here. Again, we have no equality constraints, so no h, or h is 0, whatever you prefer. We just have two inequalities. Oops. These two here. I did reformulate those already, so the g is basically the left side of those. Yeah, so we could say this is x1 plus 2x2 minus 12 and 2x1 plus x2 minus 12. All right, for the KKT conditions in part B, we need the gradient and the Jacobian, so let's compute those right away. The gradient of f, that would be, let's see, 8x1 and 4x2 minus 8. And the Jacobian of g, again, we take the first row, and compute the partial derivatives with respect to x1 and x2. For x1 we get 1, for x2 we get 2. And for the second row, for x1 we get 2, and for x2 we get 1, right? So this is a constant in that case. And that means for B, we can now write down the constraints. So starting with this one here. Means we get 8x1 and 4x2 minus 4 times 8, that's 32. So that's the gradient of f plus the transposed Jacobian. In that case, that's a symmetric matrix, so that doesn't change anything. We have two inequalities, so we need two multipliers. I'll call those y1 and y2. And that's 0. Right, so I get two equations here. Second, I just need to copy the constraints for that second part. Again, those constraints are x1 plus 2x2 minus 12 is less or equal to 0, and 2x1 plus x2 minus 12 is less or equal to 0. We don't have equality constraints, so no 0.3. 4 would be the y's are greater or equal to 0. We don't know anything about those yet, so just write down those constraints. And finally, the complementarity conditions. Just multiply that left-hand side of the inequality by the corresponding multiplier. So we get y1 times x1 plus 2x2 minus 12 is 0. And y2 times the second inequality here, 2x1 plus x2 minus 12 is 0. Right, those are the conditions. And then finally in part C, we again get a point. In this case, this is the point 4, 4. And the question is this an optimal solution, or at least a candidate for an optimal solution? Again, what we do is we substitute that into the KKD conditions. Right, so into this 1 to 5. And what we get is, let's see, first condition is 8x1, 8 times 4 is 32, plus y1 plus 2y2 is 0. Second condition is 4 times 4 is 16, minus 32 is minus 16, plus 2y1 plus y2 is 0. One more page. So that's the first condition. Now for the second one, I have to check whether the point is feasible, right? If I substitute that, I get 4 plus 8 minus 12. Well, that's 0. And that is obviously less or equal to 0, so that's fine. And for the second, I get 8 plus 4 minus 12. That's again 0. Right, so both are satisfied. For the y's, well, I don't know the y's yet. Number 5. Oh, that was number 1 here, sorry. That was number 4. What was that? Number 2. For number 5, we just computed those left-hand sides. Both are 0. Right? So 5 is always satisfied. y1 times 0 is 0, and y2 times 0 is 0. So that's true regardless of the multipliers. So that means I'm left with this first part here. Right? That's an equation system. Let me just copy that. Two equations, two y's. So from 1, I get this. And that means I can try and solve this for the y's. Solve this for, it's like 4, y1, y2. Now that's just Gaussian elimination, so hopefully you know how to do that. If you do that, what you get is y1 equals 64 over 3. And y2 is, what is y2? I didn't bother to compute that. 16 minus 2y1. Right? And my takeaway here is this is obviously, if y1 is 64 over 3, right, this here is bound to be negative. And the point is, if this is negative, then this violates one of the conditions, and that condition is the third one here, sorry, the fourth one here, that the y's have to be non-negative. Right, so that is a contradiction. 2y2 is greater or equal to 0. However, these were the only feasible multipliers. We just get those, right? No other multipliers would satisfy the other conditions. And that means that can't be a KKT point where the x part is 4, 4, because we can't find suitable multipliers for that. And that means, if that thing is not fading, that means 4, 4 cannot be an optimum. Right? So that might also be a possible solution to a problem like this. And remember, we don't know yet whether that is because no optimum exists or whether because we just picked the wrong point. At this point, both are still feasible. Question?
Well, if you solve this at the beginning, you would not have to check the other 4 conditions, right?
If you solve this at the beginning, of course, you wouldn't have to check all the other conditions. What was the formulation again? Yeah, right. Any other questions? Wonderful. So that concludes the first week of Courage Contactor. As I already said, we'll revisit that problem setting once again next week and introduce one more angle, that will be convexity. That will prove to be a very powerful constraint that will enable us to prove that a KKT point is always a globally optimal solution. And that's, of course, a very nice thing to have. So in practice, you want your optimization problems to be convex if you can achieve that, no matter how high the cost for that is. So we'll talk about that next week, and once we've done with that, we'll start basically the last topic of the semester, which is going to be integration in multiple dimensions. So exercise classes will also be here in that room, so you're welcome to stay. For the exercise classes, it would be great if we could pass through the rows again to get to you and answer your questions. For that, I marked some of the rows with these little stickers here at both ends. So it would be nice if you could just use the rows that have a sticker on the respective tables.